inverse of my winning region?
Okay, let's see. So, the inverse of the winning region basically means this other part, right, where the other player can win. And you start by saying your inverse of the winning region is a set of all states. Then we say that the inverse of the winning region we intersect with the set of all states from which the system player can enforce to go into W. So from all states we just take those states from which the system player, so in this case if W is the set of all states initially, then force of all states is actually also all states. So this would also give us a set of all states. It has to be
Q without W.
Okay, yes. So I think what you were trying to do is you were trying to solve basically a reachability game for the other player, right? Because the states from which we can stay there are exactly not the states from which the other guy can go there, right? Kind of. But I'm not sure if this makes perfect sense. I think what you... So in a sense, F doesn't appear anywhere, right? This is also a bit strange. Well, what we could do is, if you take this approach of doing it from the perspective of the evil guy, then you could say, well, also here Q without F is the initial set of bad states. And then we can say the new bad states are the old bad states and the set of states where the evil guy, so this would be a different force operator, can enforce to go into the bad states actually. And then we compute exactly the reverse, and then in the end we can build the reverse. This would work, and actually I have this also as one of the solutions on the slide. Let's see what I came up with. So my algorithm works as follows. I start by saying this set S is simply the set of all safe states. So this is our F that we had initially. And then I said the new S is the old S, but I keep only those states from which I also can stay in S. All the states from which I can fall out of S, I remove. I only keep those from which I can enforce that I stay in the safe states also in the next state. What this basically means is, first we start with this region of F states, and then I keep only those states from which I can enforce that I stay there. From this state I cannot enforce that I stay there, so this state falls out, but from the other states it's fine. So this is how my solution works. But we will come to your solution actually a bit later. So you can see actually it pretty much looks the same as our algorithm for reachability games. The only difference is basically all the unions are swapped with intersections basically, and we, yeah, that's it. Now, as before, this algorithm cannot really be written as a mu-calculus formula, because in these mu-calculus formulas we always start with the empty set of states or with the set of OR states, but we can easily also, just like before, define it in such a way that we start with the set of OR states. In the first iteration we intersect with f so that we get what we had with our standard algorithm before, and then we just refine S in every iteration by saying the new S is the old S, but only with those states from which I can also stay in S in the next step. And then, so basically we remove the states from which we cannot stay in S. We only keep the states from which we can stay in S. And of course this can be written as this mu-calculus formula now with a greatest fixed point instead of a least fixed point, because we start with the set of OR states. And as before, we can also write it with this algorithm here, and just as before, this may be a bit tricky to see that these two algorithms are the same. But essentially, everything is the same as for reachability games, it's just everything reversed, basically. Okay, so let me illustrate again how this algorithm works. We start, so here I just picked one of these three solutions. We start with our set of OR safe states, but not all the safe states may be good states, because from some of these safe states, the evil guy may be able to enforce that we have to reach an unsafe state next. And these problematic states we have to remove, just as we did it here in the blackboard. So what remains are the safe states from which we can stay in the safe states in the next step. But even there, the evil environment may be able to enforce that we have to leave this yellow region. So we remove these states and we keep only those states of S1 from which we can also enforce to stay in S1 in the next step. And this we repeat and repeat until at some point we do not remove anything anymore, and then we are done. Then we have our final winning region, and we have the set of states from which we can win this safety game, from which we can enforce that we never leave this region of safe states, this orange region. Now the same question, how can we compute a strategy that makes sure that we never fall out here into this region of unsafe states? This may not be so easy, or actually it is, but not so easy to see.
Stay in green, always.
Stay in green, yes. It's so easy that it's almost ridiculous. From all these, from this purple region, the evil guy can enforce us to go into yellow, and from yellow the evil guy can enforce us to go to orange, and from orange it can enforce us to go outside. So we must avoid that we ever get here. We must make sure that we stay in this green region. So our strategy is super simple. Whenever we are in the winning region, pick a successor state so that you are in the winning region also in the next step, because then, also in the next step, you can ensure that you win from there. So the algorithm for computing such a strategy is also pretty simple. I just take from the set of edges all the edges that remain in the winning region. Basically this means that I do not have any edges outside of the winning region, but this is not really a problem, because if the initial state is in the winning region and we always pick a successor state in the winning region, then we will never leave the winning region. So we will never reach any state that is outside of this green region. So it doesn't matter if we have a strategy outside or not, basically. So strategies for safety games are really super simple. We do not even have to store all these different iterates. We just have to know the final solution. And then, once we know the final solution, from where we can win, we just must make sure that we also can win in the next step and can win in the next step, and this we ensure by staying in the winning region, basically. Okay, so safety games are easy. Actually, you have already started to wonder about this thing. There is a connection between safety games and reachability games, because, as you already said, the set of OR states from which we can stay here is exactly the set of OR states from which the evil guy cannot reach a bad state. So, a different way for computing the winning region for a safety game would be we swap Q0 and Q1. This way, basically, we can look at the game from the perspective of the other player. Then we compute a winning region for the reachability game with goal Q without F. So we basically check from which states that evil guy can enforce to reach one of these states that is outside of this orange region. Now these are exactly the bad states, the problematic states, which we must never end up with. So this is what we get here is exactly the negation of the winning region for our original problem. So in order to get the winning region for our original problem, we just need to negate the results that we got from the reachability game. Now this may be a bit difficult to think about with all these negations, but we have already discussed this basically, and you already came up with this solution on your own. Okay, so this is safety games. They are particularly easy. And the next two games that we will briefly look at will be Buechi games and generalized Buechi games. Buechi games will be interesting for you because in the exercise you will actually have to implement an algorithm for Buechi games. So we will spend quite some time on Buechi games and touch generalized Buechi games only briefly then in the end. What are Buechi games? Here the winning condition is also again given with a certain set of states F, and the meaning of this set of states is they are accepting states and they should be visited infinitely often. Again, some examples. F is the set of states that we should reach infinitely often, and this red line here is our play, which works like this. This is executed once and then this loop is repeated. So the first case, what would you say? Is it won by the system or player or not? Totally won, yes. We visit F infinitely often, we visit F all the time, so this is perfectly fine. The next case.
It's also one.
Also one, yes, because also here we visit F infinitely often, fine. The next one. Lost, because we visit F but not infinitely often, only a couple of times and then no longer. And of course the last one is also completely lost. Some alternative form or definition of the winning condition. Let's look at an example how we can compute the winning region of a Buechi game. Let's not do this on the blackboard but directly here on the slide. So the question that we would like to answer is from which states can we reach one of the green states infinitely often? And as a first approximation, let's first think about from which states can we reach the green states at least once. This is a good approximation of infinitely often already. What about Q6? Can we reach a green state from there at least once?
No.
No. 5? Yes, because we're already there. So we have visited at least once. 4? Yes, because we can go there and then we have visited it. 3 also because we just start there. Q of course also, and the others as well. So this is a set of OR states from which we can reach a green state at least once. Now let's try to compute states from which we can reach a green state at least twice. Q6 is out of the question, right? What about Q5? No, we can only do it once and then we are out. Q4? No. The best thing we can do is either wait here forever, then nothing useful happens, or we go there and then we are out. 3 also,
Yes.
3 yes. Because here we have already visited it once and it will happen a second time. So this will be our set of states from which we can reach F twice. Now we can continue this 3 times, 4 times, 5 times. And the answer will always be the same, it will be these two states. Because if we are here, the best thing we can hope is twice and then we are done. But it is actually difficult to see that this is green. From this state here we can just visit f infinitely often, and of course also from this state here. And this will also be our basic philosophy for constructing an algorithm that computes the winning region, so the set of states from which we can reach f infinitely often. We start by computing the set of states from which we can reach the set of states f once. How can we do this with an algorithm? Right. We have already discussed reachability games, and the goal was exactly to reach a certain set of states once. So we can just reuse the solution that we had for reachability games. I abbreviated the new calculus formula for reachability games also always with reach of f. Actually, we can pick one of the three algorithms that we have discussed for reachability games. Any of these will work. Here I just wrote down one of these three new calculus formulas, but it's an arbitrary choice. I also left some blank space here, but this is just for cosmetic reasons, as you will see later. So this will perfectly work. This will compute a set of states y1 from which we can reach f once, just by doing this fixed point iterations where we compute basically these onion rings around f as we have done it on the blackboard. Now the more difficult question is, how can we compute the set of states from which we can reach f twice?
We do reachability again, and then we take some state outside of f, so we get out again, and then we do a reachability again.
That's a perfect solution, actually. I'm surprised. So what I'm claiming is what we should do is we should try to reach f once, but not in an arbitrary way. We should try to reach f in such a way that from there we can enforce to go in one of the states y1. Because from the states y1 we already know that we can reach f once more. So if we manage to reach this green part here in such a way that we can go on to y1, then we can reach f once, and from here a second time. Not from all states of f we will manage to reach y1. This red part here, from this part of f we cannot enforce to go into y1. So what we should actually try to do is, we should try to reach, not f, but f intersected with force of y1. Let me write this down. We should play our reachability algorithm, execute it again, but this time now our goal is to reach f intersected with force of y1. Because this way, when we reach this green part, f intersected with y1, then this means that we can go on to y1, and from y1 we already know that we can reach f a second time. So this we can use to compute the set of more states from which we can reach f twice. And again, we can just substitute here our formula that we had for solving reachability games. Good. Now what about reaching f 3 times? Maybe this strategy from before was not so bad. It can be adapted somehow. So from y2 we already know that we can reach f2 more times.
We try to reach f so that we can from f reach y2.
Yes, perfect. So we try to reach a state of f from which we can enforce that we go into y2 next, because from y2 we already know that we can reach f 2 more times. So that makes 3 times, right? Reaching f once and then 2 more times. Now you already start to see a pattern, but actually this first y looks a bit different, but I've left some space and I can fix this easily. So actually I can say we start with the set of all states, and just to make y2 look similar, y1 look similar to y2, I add this here. It doesn't change anything because force of the set of all states is just the set of all states, and intersecting with the set of all states does not change anything. But now our formula for y1 and y2 look the same, so we can come up with a formula for reaching fi times, and it will just be reach f in such a way that you can reach fi minus 1 times next, basically. So with this already gives us basically an algorithm. We can now compute the set of states from which we can reach f once, twice, 3 times, 4 times, 5 times, 6 times. We can go on as long as we want. But how often should we repeat this computation in order to get the set of states from which we can reach f infinitely often, not just 20 times? Yes, basically we should repeat it forever, but forever is a bit long, and in some cases we may actually be allowed to stop a bit earlier. Namely, if we ever encounter such a situation where the next result is the same as the previous result, then we could continue computing it, but we would always get the same result, the same result, the same result. So we can also stop. So we repeat this computation until nothing changes anymore. And actually this is exactly a fixed point computation, right? We repeat it until nothing changes anymore, then we have reached a fixed point. So I can also write this as a mu calculus formula. It's a greatest fixed point because we start with the set of all states and then we apply some operation again and again and again until nothing changes anymore. So we end up with such a greatest fixed point over a reachability game. And for this reachability game, we can also substitute our formula for the reachability game. So this will be our final solution, our mu calculus formula for computing the winning region of a Buechi game. I know this is quite complicated, but I hope that you at least got the basic idea how this algorithm works. Now, of course, once we have such a mu calculus formula, we can easily write down really an algorithm which implements this just with our Lego parts for the greatest and the least fixed point. This will give us such a nice algorithm here. This inner part here computes reach of f union force y, and basically the outer part then just applies this inner part until a fixed point for y has reached. But this is straightforward. You've done this already 20 times. Okay, so now we know how to compute a winning region for Buechi games. Now, the more difficult question is how can we compute a winning strategy? For this, let me repeat how the algorithm works once more. We start computing the set of all states from which we can reach f once. Then we say, well, next we would like to reach f in such a way that we can go on to y1. This makes this region, our target region, a bit smaller. And if the target region is a bit smaller, then also our final result will be a bit smaller in the next iteration. And we repeat this. Here we try to compute the set of states from which we can reach f in such a way that we can go on to y2. Now y2 is smaller than y1, so this part here will also be smaller. And if you want to reach a smaller set of states, then this will only be possible from some other smaller sets of states. So this y3 will again be smaller. And this we repeat until at some point we have this situation here, where yi is equal to yi minus 1. This is exactly the condition under which our algorithm aborts. And this means that I can redraw this picture a little bit. yi minus 1 is equal to yi, so I can make this arrow point here. So this is the situation that we have now. So our goal is to reach f infinitely often. Now, what should intuitively be our strategy to do this? Any guesses?
Using the same path all the time.
Well, yes, this may not be possible because the evil environment behaves differently all the time.
Okay.
But maybe we can use some ideas from before, from our reachability games, because after all we need to reach F, just not once, but repeatedly. So my claim is that we should go closer, 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 closer to this F part, and then once we have reached F, we can make sure that we will reach Y, I again. Because we reach F in such a way that from here we can go back to Y, I minus 1 actually, but I minus 1 is equal to Y. So once we have reached this part of F, there is a way that we can go back to Yi. And from Yi we can get closer, 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 closer to F and back. And closer, 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 closer and back. And this is can be our strategy for reaching F infinitely often. We go closer, 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 back, closer, 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 back, and with this strategy we will just reach F infinitely often. So written down formally, what we do is we completely throw away all the results except for the very last iteration of this greatest fixed point in Y, because only in this very last iteration this thing holds here. And from these R values, these are the green onion rings here in this last iteration, what we do is, just as we had it for the reachability game, from this green region here we go into the darker green region, from this to the next darker, and once we have reached the inner part, this is now new. For reachability games we were happy and we could stop once we have reached the inner part, but now we have to do something clever. Once we have reached this inner part, we just go back to Y1. And this is always possible, because this is exactly how we computed this Yi. So this is our general strategy for computing a winning strategy for a Buechi game. Turned into an algorithm. The algorithm looks actually exactly the same as for reachability games, only this line here is new. This line here says go closer, 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 and this line here says once you have reached your goal, this R1 here, go back to some state of Rn, because from there we can then reach F again, and once we have reached our goal we go back, and from there we can reach F again and again and again, and this way we reach F, which is R1 here minus this red part infinitely often. So this is the general idea for Buechi games. It's actually not very different from reachability games. The only new part is this going back so that we can reach F again. Yes, there is one more game which is a generalized Buechi game, but I'm already out of time. Am I? No, right, it's until 1:45, right?
I don't know.
Yeah. So let's go over this very briefly, because it's actually very simple. Once you have understood Buechi games, generalized Buechi games are not all too different. The difference is that now we do not have one set of states that we would like to reach infinitely often, but several sets of states, and we would like to reach each of them infinitely often. So this play would be won because we reach both F1 and F2 infinitely often. This one is lost because we reach F2 infinitely often, but F1 we do not reach infinitely often. This is also lost because we reach F2 infinitely often, which is fine, but F1 we only reach finitely often, so we do not reach both infinitely often, so this is also lost. And this is also won. We never reach F1 and F2 at the same time, but still we reach F1 and F2 both infinitely often, which is enough to win this game. The Mühe-calculus formula for generalized Buechi games looks exactly the same as for normal Buechi games. We just have one additional intersection in there. And in the algorithm, this is also pretty much the same. We just get one additional loop which iterates over the different sets basically, and we have to take the intersection of the resulting winning regions for these reachability games. This intersection is